Concordia. Yes, exactly. Okay. Let me introduce Simone Brugiapaglia, associate professor at Concordia University in Montreal, Canada, whom I had the pleasure to collaborate with during my PhD and also right now. And yeah, I will talk about nonlinear approximation and random sampling, mid-scientific machine learning, summed up in stay flexible, get lucky. Okay, so Simone, please, the floor is yours.
Grazie, Alessio. Thank you very much. Let me get rid of this pop-up thing here. Okay. Yeah, thank you everyone for being here. As said by Alessio, this I picked a kind of a maybe fancy title for this talk, Stay Flexible, Get Lucky, and I will explain to you what I mean by this in the next few slides, because there will be two main components of this talk, namely Stay Flexible is the nonlinear approximation part. Get lucky is the random sampling part. And I'll try to convince you why these are two core principles, not only in signal processing, data science, but also in scientific computing. So in the new field called scientific machine learning. So before I get started, let me acknowledge that this is work. So we're presenting work in collaboration with several very talented people, including some of which in the room, like Alessio and Caterina. And so there are too many to list in one slide. So I will just, as we go in the talk, I will acknowledge whoever the collaboration is with. So also this research was possible thanks to the generous support of several funding agencies in Canada. Great, so let's start with terminology. So the stay flexible refers to nonlinear approximation, the notion of flexibility in statistical learning theory. So let's first make sure that we're all on the same page about nonlinear approximation and define this term. So when I think about nonlinear approximation, I think about the definition that Devore does in his ACTA numerical paper, very influential, from 2008, that I highly recommend, kind of an overview of nonlinear approximation at that time. Nonlinear approximation means that the approximants do not come from linear spaces, but rather from nonlinear manifolds. Okay, so very simple idea to keep in mind. In this talk, we will focus on two main nonlinear methods, namely sparsity and deep neural networks. So the first nonlinear approximation method is sparsity, so let's define it. It's perhaps the simplest nonlinear type of approximation you can think of, because it's just, as you will see, the underlying manifold is just the union of linear subspaces. So perhaps we all know that a sparse vector, we say that a vector is sparse when most of its entries are non-zero. So you can see here the plot of the vector. Okay, only a few spikes, only a few entries are non-zero. That's kind of the intuitive image we want to have in mind. More formally, we can measure the sparsity by the so-called L0 norm that counts the number of non-zero entries of a vector. And we say that a vector is S sparse if at most S entries are non-zero, okay? We can go one step further and measure approximate sparsity instead of exact sparsity. So approximate sparsity, also called compressibility of a vector, works as follows. You want to measure how far is a vector from being S sparse, right? So if you think about the manifold of S sparse vectors, for example, that in the picture in the bottom right, this is the set of two sparse vectors in R3. Okay, so that's the union of three two-dimensional coordinate planes. Okay, so nonlinear manifold, but like barely nonlinear, because really each component is linear, and the best estimate approximation ever will measure how far your vector is from that manifold. Okay, so how far it is from being exactly as sparse. This definition will be useful later. So again, when I say best estimate approximation, think about how far am I from being sparse? And in general, here we're just talking about sparsity with respect to the canonical basis, so a vector with a few non-zero entries. But of course, more in general, you can have sparsity with respect to another basis. So maybe you have a signal like psi x, and x are the coefficients of your signal with respect to some basis psi. And now, not the signal itself is sparse, but the coefficients of that with respect to that basis are sparse. And the golden age of sparsity, so to speak, was maybe the 80s and 90s, up to the very early 2000s, where there were wavelets. So a lot of research about wavelets. If you haven't seen wavelets, they're essentially orthogonal transformations that are able to decompose natural images in a very clever way to generate a lot of approximately zero coefficients through a clever multi-scale decomposition. So on the top left, we have, for example, wavelet decomposition of an image of a castle. You can see that a lot of the pixels become black. That means they're very close to being zero. And that allows compressibility, because now you can just set all the very small coefficients to be exactly zero, don't store them in memory, and that gives you image compression. That led to the so-called JPEG 2000 compression standard that we use all the time, also nowadays. So a huge impact in computational mathematics, applied mathematics, signal processing. We have some families of wavelets here at the bottom left. Key work of those times were like 10 lectures on wavelets by Ingrid Daubechies that I highly recommend. That was kind of, in a way, the Bible of wavelets at that time. And then also a very impressive book by Stéphane Mallat, Wavelet Tour of Signal Processing, that describes applications in signal processing and beyond. However, wavelets also had an impact, and this will be a recurring theme in this talk. They had an impact beyond signal processing. In particular, they were employed successfully in scientific computing. For example, there was the family of PD methods called adaptive wavelet methods, developed by Cohen, Dam, and Devore, and analyzed in the early 2000s. They were very efficient methods to solve PDs using sparsity in a very fast and efficient way. But the story doesn't end with sparsity, because a statistician in 2006 called David Donahoe asked the following questions. So Donahoe said, the phenomenon of ubiquitous compressibility or approximate sparsity raises very natural questions. Why go to so much effort to acquire all the data when most of what we will get will be thrown away? Can we just not directly measure the part that will not end up being thrown away? In other words, Donahoe is asking the following. So let's say you're acquiring an image in an MRI, right? So you want to acquire an image of a slice of a brain, right? And then you want to compress that image, maybe in JPEG. Okay, so why do you want to measure all the pixels first and then compress the image later? Seems like a waste, right? So maybe we can directly measure the core amount of information in the image, only the relevant coefficients, without going to all the pixels first and then compress. So instead of then measure, then compress, you can maybe do them together. And that led to the so-called field of compressed sensing. Okay, so acquiring in a compressed way. So in a nutshell, compressed sensing, there's books about compressed sensing, as I will show you in a slide. But to summarize it in one slide, essentially the idea is that if you are trying to recover a sparse vector, particularly an S-sparse vector, you can do that by using a number of linear measurements that scales linearly with the sparsity S and polylogarithmically with the ambient dimension N. For example, think about an image. The big N will be the number of pixels. S will be the number of coefficients, for example, wavelet coefficients that you actually care about. So that was a great news, because that can speed up the acquisition time of many signals by orders of magnitude. And then the other good news is that after you collect these random linear measurements, that's another key ingredient of this talk, this whole recipe will work just because there's randomness involved. It's really hard, if not maybe impossible, to achieve a linear scaling in sparsity with a deterministic recipe. At least it's not known right now. So if you do these random linear measurements, then you can recover the signal by solving a program that is an optimization problem that is very efficient, such as, for example, lasso, that you might have heard of in statistics. It's actually a pretty old idea from the 80s, but here was kind of revamped and used to speed up signal acquisition. And there were two pioneering papers, one by Donahoe, from which I took this quote, and the second one by Candace Romberg and Tao. So compressed sensing had an impact not only in signal processing, like especially medical imaging, but in many other applications, include machine learning. So these are 4 books that I would like to recommend. It's a bias list, in particular the last one. I'm one of the co-authors, so it's a shameless plug. But the first book is A Mathematical Introduction to Compressed Sensing. That's a very nice resource to get started and kind of understand the theory behind compressed sensing very carefully. The second one talks about applications more broadly of compressed sensing, not only signal processing, but also machine learning, dimensionality reduction, and so on. Third one is maybe about the most successful application of compressed sensing, which is compressive imaging. So what I was mentioning before, the applications to medical imaging, for example, MRI or X-ray tomography. And finally, Again, the impact of compressed sensing went beyond signal processing as well. I will try to convince you that this idea also had an impact in scientific computing. In particular, here, the book co-author with Ben Adcock and Tatum Webster, published for SciAm in 2022, we talked about sparse polynomial approximation of high-dimensional functions, so functions that have many variables. And this will be the first topic that we'll go more in depth today. And there, one of the key ideas is, again, compressed sensing, so nonlinear approximation, sparsity, and random sampling. Okay, I told you I promised two main ingredients of this talk, sparsity and deep learning. So let's say a few words about deep learning. You know, I was talking about this wave of research, you know, the golden era of sparsity, 80s, 90s, and then compressed sensing in the early 2000s. There was another huge wave more recently that I think of as a tsunami, actually, deep learning. So it really invaded research, industrial practice. It's everywhere right now. So, and we are within the AI golden age, maybe, or one of the AI golden ages after an AI winter. But in 2012, the AI winter ended after a breakthrough on ImageNet with deep learning, very impressive classification results for images. And then there were a series of breakthroughs, more and more impressive. AlphaGo, so game playing, Amazon Lex, speech recognition, AlphaFold, protein folding, and so on. Tesla Vision, ChatGPT, of course, we'll use that these days. And then also very spectacular awards. Turing Award for Deep Learning in 2019 to 3 pioneers, to 2024 Nobel Prize to 2 deep learning pioneers. So we're really in the midst of a big wave in research, thanks to deep learning. But probably this next slide will be a bit redundant. You should, with high probability, have seen a neural network before, but just to make sure we're all on the same page, I will define it. So because we'll be talking about neural nets quite a bit. So feed-forward deep neural network is just, I think about it as a function approximator, okay, built as a sequence of affine transformations, AK, and nonlinear transformations, in particular realized by a nonlinear so-called activation. So you have a scalar nonlinear function that you apply entry-wise, right? For example, a very popular option is the rectified linear unit that gives you a piecewise linear approximant. But there are other options, tanh, sigmoid, and so on. Also, they're called networks because you can interpret the affine transformations. You know, when you have non-zero edges of a matrix, you can put edges there, and then you can interpret them as graphs, and that gives you a network. You can propagate these transformations as signals from kind of columns of neurons propagating forward, and that kind of, it's a simplified model of what happens in a brain. And that was the initial motivation also why the name deep neural networks. And deep because potentially you have many layers, right? So, and that's the depth of your network. We refer to the width as the kind of height of the different hidden layers of neurons. What you do with these networks, well, usually the goal is training them from data. So you will do that by optimizing a given loss function, potentially regularized loss function, L plus lambda R. Okay, L could be something like the mean square error loss. R could be something maybe like the L2 norm squared. In that case, in machine learning, that's called weight decay, or it could be the L1 norm. In that case, you have sparse regularization on the network. Usually, another interesting fact, usually it's assumed that the training set has some random nature. Maybe it's drawn from a random distribution. So again, randomness enters the picture here as well. And of course, nonlinearity. This is a much more nonlinear model than sparsity. Okay, sparsity is a union of linear subspaces. This is very far from being a union of linear subspaces. Much more nonlinear, mostly because of this compositionality structure that really makes the network's output depending very nonlinearly on the inputs. And like all the different techniques that we saw today, also deep learning had a profound and is having a profound impact on scientific computing. Now there's the emerging field of scientific machine learning that probably many of you somehow work on. So people propose to use deep neural networks to solve PDEs, so physics-informed neural networks, potentially in high dimensions, or for example, to discover dynamical systems from data, from time series data. Okay, so many problems that were maybe before thought of as scientific computing problems, now they're becoming kind of interconnected with machine learning, creating scientific machine learning. There's an interesting Department of Energy from the United States report, 2019, where arguably that was the first defining the term scientific machine learning. I'm not 100% sure that's exactly the first document where that was written down, but as far as I know, that's one of the first for sure. So massive needs in deep learning for scientific computing for all these applications. A lot of empirical results, a lot of impressive achievements in terms of performance. However, theoretical guarantees are limited. So this will be one of the focuses today. So after this kind of introduction, the goals for today's talk are the following. I'll try to convince you that nonlinear approximation and random sampling are very important core principles in scientific computing, in particular, and we'll show you how to leverage those via compressed sensing and deep learning. And then we'll do so through 3 case studies. First one will be approximating functions of many variables, so functional approximation in high dimensions. Second will be PD solution in high dimensions, so solving a PD where the domain is high dimensional. Third, reduced order modeling that probably this crowd is very familiar with. The focus will be to try to study methods that also admit theoretical guarantees. Okay, ideally convergence guarantee. Maybe we can prove the method converges in some way. So let's get started. First case study will be the main one. We'll spend most of the time on this one, high dimensional function approximation. So let's define the goal and the setting for this problem. The high level motivation is actually uncertainty quantification and reduced order modeling. So maybe you have a very complex model that depends on many parameters. Could be a physical model simulating, maybe some process in aerospace engineering or mechanical engineering. These parameters in the input might be affected by uncertainty, and then maybe you want to study how the uncertainties propagate from input to output, right? So that's uncertainty quantification, forward uncertainty quantification, for example. One way to do this, well, you need to sample the inputs many times to have reliable statistics on the outputs. However, this could be very expensive if your model is evaluated through a simulation that could cost hours or days of time. So what you want to do is build the surrogate model, right? To have much cheaper evaluations and then doing statistical operations much faster, computing like the mean and the standard deviation of the output through Monte Carlo simulations. So then we want to build, this means from a mathematical perspective, we want to build a surrogate or an approximation to a high dimensional function f. Okay, we'll assume to have an f whose domain is the hypercube minus 1 to the d, so d dimensions, and we want to approximate f from pointwise samples. We have our data is f of x1, f of xm. Challenge is that d could be very large, so that's the curse of dimensionality. If you're naive with the choice of the samples, for example, maybe deterministic grid, you might stumble to something like 2 to the d. So exponential dependence on d very, very fast. And we want to avoid that at all costs. Moreover, samples could be expensive, like maybe each one of them depends on the simulation. So we want to speed up. We want to devise a method that uses as few samples as possible. We'll first consider strategies to achieve this goal based on sparsity, particularly sparse polynomial expansions. So the sparsity basis will be a basis of orthogonal polynomials. So think about the 1D Legendre polynomials that you might have heard of, maybe in a numerical analysis course, and then tensorize them in multiple dimensions. Okay, so in each dimension, you consider the product of orthogonal polynomials, right? In the bottom right here, for example, we're multiplying constant by constant. You get a plane. You multiply line by constant. You get an oblique plane. Then you get parabola times constant is paraboloid, and so on, right? So you tensorize all these objects to get a multidimensional basis, which is still orthonormal. That's the beauty of tensorization. And then we want to, in this basis, we want to compute a sparse polynomial expansion. Okay, so we're going to find an approximation for which the coefficients C hat are as sparse as possible. Okay, the L0 norm that we introduced before is small. We'll focus on Legendre polynomials, but all these could, in principle, be generalized to other families of orthogonal polynomials, such as Chebyshev or the family of Jacobi polynomials. So when do we have sparsity? That's the first question. Well, we're assuming to build a sparse surrogate. Does that make sense? Well, you need some smoothness on the function. For example, a very convenient type of smoothness is holomorphic. That's not the only option, but that's the easiest thing you could, perhaps the easiest assumption you could make. Holomorphic means, in this context, that we can extend the function f in a holomorphic way to the whole complex space. In particular, holomorphic is a synonym of analytic. So if you're more familiar with analytic, just think about analytic when I say holomorphic. So if you take, for example, an 8-dimensional holomorphic function and you plot its Legendre coefficients, you get something here, the plot on the left. Okay, you can see only a few of them are very, very high, right? So above 10 minus 1, for example. Most of them are around 10 minus 6 or 10 minus 5, maybe. So you can easily neglect those. Particularly if you sort the coefficients in the second plot, these are sorted by absolute magnitude. You could say only a few of them can be retained to capture most of the energy of the function or the signal. So more formally, it can be proved, and this is due to early work by Cohen, Devore, and Schwab in approximation theory and follow-up papers, that if your function is holomorphic in a so-called Bernstein polyellipse, then you can recall that best external approximation error guy that I told you before about. Well, you can have an explicit upper bound to the best external approximation error. You can prove how fast the approximation error goes to 0 for S that grows, okay? So in particular, the best external approximation error for such functions will be going to 0 exponentially in S to the 1 over D. There are also other types of decay rates that are algebraic as opposed to exponential, and they are also dimension independent. In this talk, I will show the exponential ones because they're just easier to read, I would say, from a typographical perspective. But everything can also be now with those other types of rates. So this begs the question, okay, holomorphic gives sparsity, great, but is holomorphic reasonable? So isn't maybe an assumption that is a little bit too strong? And I want to convince you that, yes, that's a reasonable assumption, in particular, because it arises in many parametric physical models. For example, these are models that are considered, for example, by engineers or more applied people, such as parametric PDEs, okay? Parametric PDEs, such as, to keep simple examples in mind, maybe the harmonic oscillator, the diffusion or heat equation, or a PDE on a parametric domain, right? So that's your PDE operator, L, and it depends on some parameters, mu. To keep a more tangible example in mind, very simple, the parametric diffusion equation here on the bottom left, I have classical diffusion equation, but there are some parameters in A, okay? The diffusion term depends on the parameter mu. That's why this is a parametric problem. Therefore, the solution will also depend on mu, right? So you'll fix a mu, you solve the PDE, you will have the dependence. That's called the parameter to solution map. Mu parameter maps to solution mu of mu. And for example, for this problem, you can formally prove that this is a holomorphic map under pretty mild assumptions. For example, when A is piecewise constant on the physical domain, this is a funny problem called cookies in the oven. Okay, you're warming up the cookies, 8 subdomains there are the cookies, and maybe each cookie has slightly different ingredients. So the diffusivity through the cookies will be slightly different. And you want to kind of model this uncertainty by playing with a piecewise constant diffusivity term. Another family of problems that we've recently been working on with Alessio is parametric problems on graphs. Parametric dynamical systems of graphs in particular, such as graph diffusion. If for graphs that have a community structure, think about social networks, maybe where circles of friends, and where you can run a diffusion equation on a graph, like a network, which works with principle is similar to a heat equation, but now in a discrete environment. If you have that, for example, the diffusivity is piecewise constant, like in this PDE problem, but now in the graph scenario, so information or whatever the quantity that is flowing on the graph depends on the communities like uniformly, right? So if the diffusivity will be the same for any point from community 1 to community 2, or if you're flowing information within a community, then you have always the same diffusivity. Using that type of assumption, then you can also show that the parameter solution map is holomorphic formally. So again, this is an assumption that arises in several modeling scenarios that you might consider. So how do we actually go about computing a polynomial approximation? Well, now that's where compressed sensing comes to help us. I will present, like, again, in one slide, a method that actually has been developed over now more than a decade. The first paper was by Dustan and Hawadi, 2011. And then there were many developments from there where people were using compressed sensing to build like efficient surrogate maps for parametric models. So again, random sampling, we'll draw our samples IID at random from the hypercube -1, just fully at random, okay? M totally uniformly random points from there. Then you take a condition set for your polynomials, okay? That's a slightly technical thing, but when you're in high dimensions, you have to make choices about the degree of each polynomial in each dimension, right? In 1D, it's easy to just truncate 1 degree. But if you tensorize, you might need a higher degree on 1 dimension, a lower degree in another dimension. So it's a bit trickier to truncate in higher dimension. And if you use truncation sets like this is the space of polynomial degrees. For example, in dimension 1, you go up to degree 8. When in dimension 2, the degree is 0. You go up to degree 4 when the dimension 2 is 1, and so on. That's called a hyperbolic cross degree set. So, for example, if you take a truncation like that, and if you compute the coefficient of the polynomial by solving a compressive sensing problem, in particular here I'm using a weighted square root lasso problem. These are slightly technical addition. It's not enough to just solve a vanilla lasso problem to beat the Cursor dimensionality in general. In this case, you really need to use weights. So the L1 norm will be just the sum of absolute values of the coefficient. You also have some weights that are the L infinity norms of the polynomials, in this case. And square root lasso, because if you remember from the lasso, there was a square here. Now there's no square here. That's why it's called square root lasso. And this has beneficial properties in terms of stability of tuning this parameter lambda with respect to the noise affecting the data. Anyway, so you can prove, again, focus on theoretical guarantees. We were able to prove in the book that you can provably lessen the Cursor dimensionality if you use compressive sensing to approximate a d-dimensional function with this type of scheme. So if f is holomorphic, and if you define this m tilde, which is just the number of samples divided by a bunch of log factors, and importantly, there's a log d here. So the dependence on the dimension is only logarithmic, it's not like exponential. And if you use a hyperbolic cross to build your approximation, then with high probability, because this is a randomized method, the samples are random, so that all statements will be in probability, you can prove that the approximation error, so ground truth f minus the approximation f hat, scales almost like the best external approximation error, which was the ideal benchmark. We have the same type of exponential decay. We only have a difference here, a factor 2. So we call this a quasi-optimal convergence rate, because we recover almost the optimal rate of the best external approximation. So to summarize, compressive sensing can provably lessen the Cursor dimensionality if you're trying to approximate a high-dimensional smooth function with polynomials. Key assumption is holomorphic, which implies compressibility, and that arises naturally, such as in parametric models, PDEs, or graphs. Random sampling is key. There's no deterministic recipes that are known that can achieve the same thing with provable convergence rates. Great. We're talking about sparsity and compressive sensing in high-dimensional approximation. What about deep learning? Well, of course, you can also approximate functions with deep neural networks. And classical deep neural network approximation theory usually relies on something that you might have heard of, universal approximation theorems. It's a very famous keyword these days. They can, by the way, be proved also for other techniques. There's just something of deep learning. It can also be proved for polynomials, and that's the Weierstrass theorem. So, but for deep neural networks, usually they establish conditions on the architecture of the network, such as you can accurately approximate your functions from a given class you care about. And initially, people were considering, like, for example, continuous functions and shallow networks in the 80s, and proving universal approximation theorems for those classes. Then there was a pretty influential work by Jarodsky in 2017, where there were universal approximation theorems for deep ReLU networks. And then there were many, many extensions. This is a pretty active area of research where people developing more and more general universal approximation theorems for like function in solvable spaces, k times continuously differentiable, holomorphic like we do here, cartoon-like, and so many fancy classes of functions. This is a nice review paper that you might want to take a look at. It's not fully up to date because now it's from 2021, but it's a nice entry point to the topic. These are great. However, they do not address certain key questions. Particularly, they don't tell you anything about data and training. So, we can prove that a deep neural network exists that approximate function from a given class, but how do I obtain such a network from training? Can I obtain such a network via training? Also, how much data do I need to do so? So these are two key questions for practical applications that we will address through the technique of so-called practical existence theorems that will be an enhanced version of universal approximation theorems. That will not answer these questions perfectly or reducing the theory to gap practice ideally, but still will be one step forward to say a little bit more about those. So that's spoiler. That's how a practical existence theorem looks like. Then I will give you, a sketch of the proof very quickly. And this was a theorem in a different version, first published by Ben Atko and Dick Dexter. Then we improved it also with Sebastian Moraga, a later paper. That's the version I'm showing here. So again, F holomorphic in a bursting polyellipse. This M tilde is the number of samples up to log factors. Then you can you can show that there exists a class of ready DNNs for which you have depth, width bounds, and like number of trainable parameters bounds, and everything scales nicely in the number of data points, namely at most polynomially. You don't have any exponential dependence there. Second, we show that there exists a sparse regularizer such that the following holds. If you train your network from this class by minimizing this root mean square error loss plus the regularization term, then you can prove that with high probability the same type of error bound as we were able to prove in sparse polynomial approximation holds now for deep neural networks. So in a nutshell, this theorem shows you that deep learning can provably do as well as sparse polynomial approximation. Unfortunately, this theorem will not be able, we'll see in a moment in the proof why, but this theorem is not able to prove you that, to show you that deep learning can do better than sparse polynomials, but only as well as sparse polynomials. But of course, it doesn't exclude that it could do better. Okay, this is kind of a worst case scenario type of upper bound. I'm presenting here for the scalar valued case, the theorem. We're going to extend this to Hilbert, Banach valued functions. I'm not talking about noise in the samples, but you can add noise to the samples, then you will have an extra term in the error bound. You can add the optimization error, so maybe you don't fully minimize this, you minimize up to a certain tolerance, and then you will have an extra term here and so on. You can extend this to functions of infinitely many variables. Although in that case, this decay rate doesn't work because the infinity doesn't make any sense anymore here. So you will have a different decay rate, which is algebraic and independent of the dimension. So to give you a quick sketch of the proof, that's the only proof sketch I'm going to present today. At a high level, it's pretty simple. Then there's many technical details that I'm conveniently sweeping under the carpet here. But keep in mind the following. That's the ReLU class. The ReLU deep neural network class is defined as follows. Keep in mind that figure. Okay, so there's a bunch of modules, phi mu delta. Each of these are networks, individual network modules. Each of them approximates a Legendre polynomial. So first you construct a bunch of networks, ReLU networks. They're able to accurately approximate Legendre polynomials. In particular here, we need with respect to the L infinity norm. Then you parallelize all these modules. Okay, you assemble a bigger network that stacks all of them one on top of each other. And then you connect everything through a last linear layer. You can see that just realizes a linear combination of networks, right? So this big network is doing a linear combination of network modules that emulate polynomials. So this whole network as a whole is emulating the polynomial approximation scheme that we saw before. That's the main idea of the argument. And now you can put you can put the data into your modules. This will give you the sampling matrix. And then you have a square root lasso problem. So that training program that I showed you before, that becomes essentially it's equivalent to a square root lasso problem, where we're almost in the setup that we did before, where we did compressive, but now instead of evaluating orthogonal polynomials, we're evaluating at random data. We're now evaluating non-orthogonal neural networks on random data. So that's the main technical thing. You have to make sure that the fact that you break orthogonality, for example, still is fine. Everything works. So by the end of the day, by checking many technical details, you can show that the approximation theory for sparse polynomials also applies in this case to a careful perturbation analysis. Therefore, you can have that error bound. Also, interestingly, the network is sparsely connected because the first modules are sparsely, the polynomial modules are sparsely connected. Those promote sparsity or compressibility in the last layer. So in particular, the sparse regularizer will only sparsify the last layer. Also, one important disclaimer about the argument is that from the first to the second last layer, they are explicitly constructed, so like initialized in a deterministic way. And then the last layer is trained from data. That's how the argument works. Now, you can put this to the test and compare, for example, deep learning with compressed sensing in a 30-dimensional parametric diffusion equation on a 2-dimensional physical domain. And this is what you get. For example, if you plot the decay of the L2 error and the H1 error as a function of the number of samples, okay, so the solid line is compressed sensing or sparse polynomials. That's the decay of compressed sensing. All the dashed lines are many deep learning setups, okay, with different activations. There's ReLU, there's leaky ReLU, there's TANH, and different architectures. Like here, 1 per 10 means depth 1 with 10, and like different depth, like depth 2, depth 3, depth 4, and so on, like different types of architectures. So if you're careful now, if you compare compressed sensing with all these deep learning tuning strategies, deep learning strategies with different tuning parameters, then if you're careful here, for example, with the TANH activation, you can outperform compressed sensing in this case. So if you're careful with the parameter tuning, you can even do better than sparse polynomials. So the theorem tells you that deep learning can do as well as sparse polynomials, but if you're careful in practice, you can even outperform it. That's one takeaway of this experiment. In the interest of time, I'll just mention quickly, not go into too much details, but like you can also extend or carry out this analysis to different class of functions, the frequency localized functions that are localized in the frequency domain. And you can prove a practical existence theorem for that class, where interestingly, in that case, for those functions, the bandwidth of the frequency is a key parameter. This is work in collaboration with Martina Neumann, Anders Lerma Pineda, and Jason Bramberger. You can prove that in order to accurately approximate those functions with a deep neural network, you need a number of samples that scales like this with the bandwidth. So we were able to explicitly track the dependence of the bandwidth of interest in the sample complexity. In this case, we're low dimension, though. The theorem only holds for dimension up to 3. And another thing, instead of orthogonal polynomials, we use the so-called Sleppian basis, which is like a basis localized in frequency and space. That concludes the part about high-dimensional factor approximation, which gives you like the main conceptual elements to understand practical existence theorems. Now we'll more quickly see how that can be proved also in the case of PD solvers, when you're approximating a PD in high dimensions, and when you are building a reduced order model. So PD solvers, first I want to raise a bit of awareness. This is a slide about kind of works that I think are relevant when you're solving PDs with sparsity or compressed sensing and deep learning. On the right column, deep learning, we all have probably heard these days of physics-informed neural networks, PINs, very popular method to solve PDs through neural networks that kind of repopularized an idea from the 90s that is, again, using a deep neural network to emulate a solution to a PD. Deep learning can also be used to solve high-dimensional PD. And high-dimensional PDs, maybe I don't know how many of you guys work with high-dimensional PDs, but they usually come from motivations in applications in finance, such as the Black-Scholes model, or computational chemistry, such as the Schrödinger equation, where you have many variables, not just a physical domain. In fluid dynamics, you have a physical domain up to 3 or 4 dimensions if there's time as well. But in these applications, you can have 10, 20, 30 or more dimensions for the physical domain. On the sparsely compressed sensing side, there were first adaptive finite elements or adaptive wavelet methods, which essentially rely on sparse approximations, but where the sampling is adaptive. Then there were some works working on compressed sensing for PDs. One is the compressive Galerkin methods proposed in 2010. This was a coursing method based on Petro Galerkin that I worked on in my PhD thesis back in Politecnico di Milano with Stefano Micheletti, Fabio Nobili, and Simone Perotto. Then Dobeshi and other collaborators proposed sparse spectral methods based on Fourier Galerkin, and recently applied to very high dimensional problems, they can go to up to 1,000 physical dimensions, which is pretty crazy. By many tricks. You have to apply many clever tricks to achieve that, but it's possible. And finally, compressive spectral collocation methods that we will talk about here, proposed together with my former postdoc, Wei-Chi Wang. So again, high-dimensional PDEs, motivation, computational chemistry, and finance for optimal control. The model problem would be a high-dimensional diffusion reaction equation on the torus. Okay, the torus is just the hypercube with periodic boundary conditions. Okay, so we'll be in a setting with periodic boundary condition just to have our life simpler, to be honest, so that the analysis is simpler and we can use a Fourier basis. There's no this is not a fundamental restriction. You could do that in a non-periodic domain, but the constructing the basis will be you have to be a bit more careful. You have to use stuff like boundary adapted orthogonal polynomials. Anyway, if you use Fourier and periodic boundary conditions, that's your spectral basis. You truncate in a hyperbolic cross like before. We pick m random collocation points from the torus, like before, so random sampling is key. Then we assemble the stiffness matrix by evaluating the PD operator at the basis functions at the collocation points and the forcing term at the collocation points. And we solve via, for example, square root lasso or other sparse recovery problems. Then with Wei-Chi, and then also later with Nick Dexter and Samir Karam, we were able to prove that compressive Fourier collocation is able to recover the best S-term approximation with respect to the Fourier basis, like our target was before, in a hyperbolic cross, using a number of samples that scales logarithmically with respect to the dimension of now the physical domain. Okay, so this is the dimension of the domain to the PDE here. So we're happy because this is a proof that this kind of technique, the compressed sensing, particular compressed Fourier collocation, can lessen the curse of dimensionality. And then you can apply this to deep learning to prove a practical existence theorem for deep learning here as well. The construction here has some more technical elements. Particularly, we use a periodic layer that enforces by design periodic functions. It's just essentially there are a bunch of Fourier features in the first layer, if you're familiar with this language, that enforce periodicity. And then we also use ReLU activations with just ReLU to the power L with L greater than or equal to 2. That allows you to replicate products exactly. And in particular, you're able to replicate through applying a bunch of trigonometric identities. You could be able to construct the Fourier basis explicitly with such a network. So we can then apply the theory for compressive Fourier collocation to prove that periodic pins inherit the convergence properties of compressive Fourier collocation. In particular, you can recover the best S-term Fourier approximation error using a number of samples that depend only logarithmically on these. So again, we're able to provably show that pins can lessen the curse of dimensionality, something that you can see in practice as well, because here we're plotting the relative approximation error as a function of the number of sample or collocation points for different dimensions. Okay, the domain is dimension 6, 10, 20. You can see the decay mildly depends on the dimension. It's not like you get a much bigger constant when you go up, when you double the dimension, for example. And finally, reduced order modeling. How do we prove a practical existence theory for deep learning and reduced order modeling? Here, the context we will consider is a so-called autoencoder-based DL-ROM, deep learning-based reduced order modeling, that you might have heard of. That's something developed over these papers, and a group from MOX, Polytechnic Milano, has been working a lot of these kind of methods. So now we have a parametric PDE, right? So the full order model, so the PDE depends on some parameters, like in our initial slide. We discretize the domain, and then we have a full order model that will map a parameter in the parametric space to a particular solution associated with those parameters. Okay, so this is a discretized solution to a PDE, for example. How do you do this with deep learning? Well, you want to approximate this map, parameter to solution map. You do this by training a neural network from snapshots. Okay, snapshots are just instances of the parameters, and then the corresponding solutions for those instances. And usually this will be random, selected at random. And then you train an autoencoder to do the following. So we first find a clever latent space. So essentially we compress the so-called solution manifold, the set of solutions for all the parameters that range in the allowed domain. We found a latent space that is able to kind of compress the main features of this solution space or solution manifold. So the encoder compresses the solution space the decoder kind of gives you back the solution from the latent variables. After you do this compression, you train a reduced DNN module that learns the map from the parameters to the latent space corresponding to that solution. Once you do that, usually the dimension of the latent space is much lower than the dimension of the discretized solution. Otherwise, there's no compression going on. And usually you throw away the encoder after you train it, and you just use the decoder and your autoencoder-based DL-ROM. Okay, that's a technique, again, developed over the years that we were able to analyze together with Nicola Rares-Franco from MOX, Politecnico di Milano, where for simplicity, we took a 1D physical domain. You can expand this, but there's some technical non-trivial elements that you have to take into account. We discretize that with an equispace grid, and then you have a d-dimensional parametric domain that associates parameters mu to solution u mu that lives in a solid space HS. Then we're able essentially to prove that the DL-ROM approach is able to give you, if you use m uniform IID snapshots, is able to give you an error that again scales like this, best external approximation error, like we've seen many times today, plus this interesting term that links the dimension of the latent space with the regularity of the solution S. So in particular, this tells you if the solution is smoother, then maybe a latent space that is smaller is okay. Otherwise, if you have less smoothness, you have to pick a larger latent space. So this is like the extra feature of this analysis that is interesting. And the theorem, the only network that is trained from data is phi, the reduced module. The autoencoder and the encoder and decoder are explicitly constructed. In particular, phi is convolutional. So psi is convolutional, like people use in practice. So discussion, we have seen a bunch of practical existence theorems today. They are enhanced universal approximation theorems that involve deep neural networks trained from data. Hopefully, I convinced you that the proof strategy is flexible. We have used different problems like functional approximation, PDE solver, reduced order modeling, different basis functions, different approximation methods. So if you have another problem for which you're able to prove a universal approximation theorem, but you would like to go one step further and prove something about training and data, you might be able to be in a position where this is applicable. So come speak to me if you want to talk about this. There's also other families of theoretical guarantees that are statistical learning generalization bounds. They're also very powerful. The thing about those is that they usually, all the layers are trained for those. However, they're typically stuck with a Monte Carlo rate, something like n to the minus 1/2. So it's really hard or / unknown how to prove faster rate for this kind of statistical learning approaches like exponential we have here. There is some recent work exploring connections between minimax optimality, which is like more statistical learning, and optimal recovery, which is what we've been talking about here by DeVore and collaborators. Some caveats, limitations. Only last layer is trained in the PET. This is a gap between theory and practice. There's a way to kind of relax that thing and prove in a recent paper by Benacco, Nick Tester, and Sebastian Moraga, prove the existence of uncountably many good minimizers for which you have fully trained deep neural networks, so not only the last layer. However, you don't prove that all the minimizers are good, but only uncountably many of them are good. Moreover, as I told you before, PETs can show that deep learning can achieve the same accuracy as some other reference methods, such as compressed sensing or least squares, but they could do better in practice. That doesn't mean that's kind of a worst case recovery scenario. So to conclude, in the last 1.5 minutes, hopefully I convinced you that nonlinear approximation and random sampling are powerful core principles for machine learning and scientific machine learning, particularly through compressed sensing and deep learning to approximate functions, PDE solvers, and reduced ordered models. And there is an interplay between compressed sensing and deep learning through the theory of practical existence theorems. This is not the end of the story. There's many research directions I've been working on, and I'm working on as we speak here, connections between deep learning, compressed sensing, and beyond. For example, you can do compressed sensing with generative models, where instead of sparsity, you assume that an image, for example, is generated by a deep network. You can design interpretable deep learning architectures via unfolding iterative algorithms and interpret each iteration as a layer. You can leverage the theory of sparse polynomial approximation in EDMD, extended dynamic mode decomposition, which is done to learn a dynamical system from data. Also, you can use compressed sensing for eigenvector approximation, not only to approximate functions, but also to approximate in a fast way eigenvectors from very, very large, low-rank matrices. Moreover, there's some negative results. Also, together with Alessio, we proved some so-called impossibility theorems for binary classification problems where deep learning is provably impossible for deep learning to learn certain functions called identity effects, where you classify if two things are identical or not. Finally, two last directions. We've studied with some people at GSSI connections between a phenomenon called deep neural collapse, where the hidden representations of the layer tend to cluster together, and the low rank bias in deep learning, that is, during training, weights tend to have low rank. These are two things that are documented empirically. We have some theory that tries to connect these two. And finally, with Caterina and Alessio, so check it out tomorrow. There will be a seminar about this. We're exploring connections between generative modeling and regression. So there will be an interesting seminar by Caterina tomorrow. Thank you very much for your attention. This is the list of references, and I'm happy to take any questions.
Thank you, Simone. Thank you so much for the interesting talk. Are there any questions in the audience? Or even online?
Even easy questions. Don't be afraid. You know, even could be a very simple question. I won't judge you. Yes.
So maybe I can start. Thanks a lot for the very interesting talk. I have one question. So actually, at the beginning, so I'm not very familiar with the, let's say, sparse.
Sparse
kind of
sure, no problem.
So my question was, now you have this coefficients, let's say, for the polynomials.
Yeah.
So, and you were showing like exponential case.
Case, right? Yes.
Yeah. So do you have like something similar to the reduced basis problem when you have, let's say, I don't know, fast decay or slow decay?
Yeah, it's similar. Yeah, here's a bit different because in that case you might have maybe in reduced basis you're really using one linear subspace to approximate, like the space spanned by the reduced basis. You could do something similar to reduced basis with sparsity. Actually, that's something that I'm not sure if it's been done, but like it would be an interesting thing to explore if it hasn't. You could also have a sparse combination of maybe a larger reduced dictionary, just maybe instead of a basis, right? So here you have a nonlinear approximation rate. Usually in reduced basis, you have a linear approximation rate, which is, I guess, related to the Kolmogorov width, right? So that the approximation theory concept there. Exactly. Yeah, that goes. It's similar here, although here we're doing a nonlinear approximation in the sense of this, right? You're approximating in a manifold and union of cleverly chosen subspaces.
Nice.
Yeah.
Just a brief curiosity about the approximation quality. So again, there will be exponential one.
Yeah.
Like it is the same. Is it the same as the 1D case where if it is Sobolev, then it becomes polynomial in
yeah, this is exactly the generalization of
is like sub.
It is
like
yes, it is. This is a okay. This could do it dimension 1, right? So in 1D this would be S.
Yeah.
So if you have an analytic function, you get an exponential rate. That's kind of something very well known in numerical analysis. If you approximate an analytic function with polynomials, you get exponentially fast, so-called spectral convergence. You could have Sobolev regularity, yes, so it's a bit lower. You get algebraic rates with faster and faster exponents. Yeah, you can also do that in higher dimensions. You need to define something called mixed Sobolev regularity, where you have regularity of mixed derivatives.
And you say that the results are similar also for those.
Yeah, you can achieve. It's not like those haven't been written down completely. There are some papers that start doing this, but it's more like for holomorphic regularity. There's a lot of papers now. It's very well developed. For Sobolev mixed regularity and compressed sensing, is like it's starting to get there, but like it's we don't have a full kind of theory like for holomorphic.
In theory for results.
Yeah. You can observe these rates. Yes.
I have a curiosity about the uncountably set of solutions.
Yeah, I mentioned that. Yes,
that's actually very interesting. So, like, what I was wondering is that So does that mean that actually the optimizer has a good shot at like minimizing, like I mean, like at getting a good training behavior just to get to the
Well,
one of those good minimizers?
yeah, ideally, yes. Although in this argument, they show that these uncountably many good minimizers are those for which the loss is that these are actually interpolating. So the loss is actually zero at these minimizers.
Okay.
And they're uncountably many, although we have to be careful because the training space is very large, right?
Yeah,
So
yeah.
uncountable. So I think the measure,
But still, if you have uncountably minima, like that means that like there should be, or I don't know if
I don't know if
you
they
can quantify that there is a
yeah.
high chance
in
that
the
you can-
paper they didn't do that, like the probability of what is the probability of landing in a good minimizer.
Yeah.
I don't think they have proven that if I'm not mistaken. That could be interesting to look into. Just prove that there exists uncountably many good minimizers, but not quantifying what's the probability of landing in one of those, which we're actually very interested in.
Great.
Yeah.
Okay. If there are not any other questions, I will thank